Today I will discuss about the Sommerfeld theory, de Broglie's equation, Heisenberg uncertainty principle and Schrodinger wave equation. As you know, there are so many theories, equations to understand for the complete structure of the atom. So, these theories and equations will be very much helpful for understanding the atomic structure of the element. Sommerfeld theory. In 1915, Sommerfeld extended the Bohr's work by specifying that the electrons travel in the elliptical orbit with nucleus at one of the foci. As the orbit broadens, the length of the two axes become closer. As soon as they become equal, the orbit becomes closer. Thus, the circular orbit is only a special case of elliptical orbit. These are the shapes of the orbitals. Various positions and dimensions of the elliptical orbitals according to different values of the quantum number. The electrons, while travelling in an elliptical orbit, the momentum of the electrons may be resolved in two components, one along the radius vector and other at right angle to the angular momentum. This is the figure showing the elliptical shape of the orbit. The latter is given by the expression kh upon 2 pi, where k is an integer and is called the azimuthal quantum number. In the same way, the momentum direction of the radius vector is called radial quantum number and represented by an r. Using these two momenta, the equation E n is equal to minus 2 pi square m z square E 4 upon n square h square may be written as E is equal to minus 2 pi square m z square E 4 upon n r plus k square into h square, where n r plus k is equal to n is called the principal quantum number used by Bohr. It can be proved that the ratio of n to k is same as the ratio of the major to minor axis of an elliptical orbit in which the electron is supposed to revolve. Thus, n upon k is equal to length of major axis upon length of minor axis. The azimuthal quantum number k n values for principal quantum number n with n, n minus 1, n minus 2 and so on. K cannot be 0, since in that case the minor axis of ellipse would be 0, that is elliptical orbit would be reduced to a straight line passing through the nucleus of the atom. But experiment and theory show that one of these values can have 0 value. Thus, k has been replaced by L, where its values are from 0 to n minus 1. The velocity of an electron is not uniform in an elliptical orbit. The velocity of electron is greater in its perihelion position closest to the nucleus than in its aphelion position farthest from the nucleus. The velocity variation will cause difference in the effective mass of the electron at different position in its orbit. According to the theory of relativity, the effective mass m of the particle moving with a velocity v may be given by m is equal to m0 under root 1 minus v square upon c square, where m0 is the rest mass of the particle. Taking into consideration this relativistic mass change, the energy of electron in a hydrogen like atom is given by the equation E is equal to minus 2 pi m z square e to the power 4 upon n square h square into 1 plus alpha square into z square upon n into 1 upon k minus 3 upon 4 n, where alpha is equal to 2 pi e to the power 2 upon h c is equal to 1 upon 137 is the fine structure constant. In this way, Sommerfeld subdivided Bohr's original stationary orbits into several subshells which slightly differ in energies and are characterized by differences in orbital shapes. There are limitations of Sommerfeld's theory. Although Sommerfeld's elliptical orbits explain the fine structure of the spectra of hydrogen, helium, lithium, etc., even then this theory fails to explain Zeeman effect and star effect, the correct number of the lines of the spectrum, information about the relative intensities of the lines whose frequencies alone is predicted. The fundamental idea of wave mechanics is that the wave nature of matter, or we can say that a small particle like electrons, protons, etc., when in motion possess wave characteristics of wavelength. Wave frequency and wave amplitude, besides the particle characteristics of mass and momentum, some of the principal aspects are described here. In 1924, de Broglie stated that the electrons, like light, have a dual character, wave nature and momentum mv of a particle in motion is inversely proportional to its wavelength. Hence, mv is directly proportional to 1 upon lambda, or mv is equal to h upon lambda, where h is the Planck's constant. De Broglie equation may be proved as follows. Let a photon has frequency nu, then its energy E may be given E is equal to h nu. If a particle of mass m moves with velocity c, then its energy may be given as E is equal to mc square, and we know that E is equal to h nu, we get h nu is equal to mc square. Since photons travel in a free space with velocity of light c, its momentum mass into velocity p may be given as p is equal to mc. P is equal to mc by dividing equation this h nu is equal to mc square. Then we can get this h nu upon p is equal to c. P is equal to h nu upon c is equal to h upon lambda, or lambda can be represented as lambda is equal to h upon p is equal to h upon mc. If a particle of mass m moves with a velocity v, then the equation will be given below. A lambda is equal to h upon mv, which is de Broglie's equation. According to de Broglie theory, the concept of orbit and energy distribution around the nucleus takes an altogether different form. The theory further stresses that the electron is no longer a point mass moving in an orbit, but is instead a standing wave train extending around the nucleus in a circular form. For a wave to remain continuous in phase, the circumference of the orbit may be given as 2 pi r is equal to n lambda, where r is the radii of the orbit, lambda is the wavelength, and n is a whole number. According to de Broglie's equation, lambda is equal to h upon mv. On substituting the values of lambda in equation, 2 pi r is equal to n lambda, 2 pi r is equal to nh upon mv, or mvr is equal to nh upon 2 pi. Evidently, the above equation is the second postulate of Bohr's theory. Thus, de Broglie's relation provides a theoretical basis for Bohr's postulate. An electron of mass m and velocity v has kinetic energy half mv square. An electron of charge E is accelerated by an applied potential V has kinetic energy VE. On combining these two relations, kinetic energy is equal to half mv square is equal to VE, or V is equal to 2 VE upon m to the power half. According to de Broglie's equation, V is equal to h upon m lambda, lambda is equal to h upon 2 VEm to the power half, or h upon m lambda is equal to 2 VE upon m to the power half. On substituting different values, we get lambda is equal to 6.626 into 10 raised to the power minus 34 joules second upon 2 into 1.602 into 10 raised to the power minus 19 C into 9.109 into 10 raised to the power minus 31 kg into V to the power half equal to 12.26 into 10 raised to the power minus 10 V to the power minus half meter. It means as the value of V changes, wavelength changes. If V varies from 10 to 10,000 volt, lambda should varies 3.877 angstrom to 0.1226 angstrom. This is the order of wavelength of X-rays. It is well known that crystalline solids can act as diffraction grating for X-rays. Therefore, if de Broglie's concept of dual behavior of electron is correct, the crystalline solids should also act as diffraction grating for a beam of electron, which has been verified experimentally by Davison and Germer. In 1927, Davison and Germer performed an experiment. They emitted electron from a hot tungsten filament and were accelerated by a potential ranging from 40 to 68 volt. Now, these accelerated electrons were allowed to strike on nickel crystal. Since nickel crystal act as a grating, the electron got scattered and were received on a photographic plate on which the electron produced diffraction ring. This is the pictorial presentation how they did their experiment, and heated tungsten filament, and then electric field was applied, nickel crystal as grating, and accelerated beam of electron, then photographic plate it is shown. These rings were found to be similar in those produced by X-ray when they are diffracted by the same nickel crystal. Since the wave nature of X-ray is well established, hence electron also should have a wave nature. Thus, this simple experiment gave direct evidence for the wave nature of electron. The dual character of matter is only significant for microscopic particles. As the mass of the particle increases, the wavelength decreases. It may be so small for bigger particle that it can be measured. In other words, we can say that macroscopic bodies have no de Broglie wavelength. Electromagnetic waves and matter wave are totally different. Their differences are given in the following table. Distinction between electromagnetic wave and matter waves. In this table, the property electromagnetic waves and matter wave has been characterized like this. Property, nature, electromagnetic wave. These waves are associated with electric and magnetic field and are collectively known as electromagnetic waves. These are from radiant energy. Matter waves. These are due to moving microscopic particles and have wave character, therefore known as matter waves. Velocity. Electromagnetic waves, all these waves travel with velocity, that is 3 into 10 raised to the power 8 meter per second. Matter waves, these waves travel with different velocities which are less than, that is 3 into 10 raised to the power 8 meter per second. Medium of the propagation, electromagnetic waves are able to pass through vacuum. The direction of propagation is perpendicular to both electric and magnetic field. Matter waves, these waves are not able to pass through vacuum. The direction of propagation is not related with electric and magnetic field. Significance, electromagnetic waves, these have physical significance as their wavelength could be easily observed and measured. Matter wave, these waves have physical significance only for microscopic particle and not for macroscopic particle. In 1927, Heisenberg proposed his uncertainty principle. According to it, it is impossible to determine simultaneously and precisely both the position and momentum of a microscopic moving particle like electron or proton. Mathematically, it may be expressed as delta x into delta p is equal to h upon 4 pi, or delta x into m delta v is equal to h upon 4 pi, where delta x is uncertainty with respect to the position, delta v is uncertainty with respect to velocity, m is the mass of the particle, delta p is uncertainty with respect to momentum, and h is the Planck's constant. Evidently, if delta x is very small, that is the position of a moving particle is known more or less accurately, delta v or delta p would be large, that is uncertainty with respect to velocity will be large and vice versa. To explain this principle, let us consider an electron moving in a circular path. A photon of wavelength 1 angstrom, that is photon of high energy, strikes on electron, some of its energy transfer to the electron, thus the electron changes its path. In other words, electron does not move on circular path as expected. Due to change of path of electron, its velocity also changes, and hence the determination of the exact velocity becomes impossible, although the measurement of the position or the location of the electron is certain, since it can be observed by means of microscope. Now consider the photon of light of wavelength greater than 1 angstrom, that is photon of low energy, strike on electron. It is unable to change the circular path of the electron, therefore velocity of electron is not changed. Thus this pictorial presentation can be shown over here, that the change of the path of the electron by, this is the microscope, photon of the 1 angstrom and origin of the path of the electron and expected path of the electron. In this condition, the determination of velocity of electron is possible, but the position or the location of electron cannot be determined accurately. Evidently, the exact determination of the position or velocity of the electron cannot be made simultaneously. Hence, the idea of definite orbits has no meaning as suggested by Bohr. Now, in place of definite orbits, we can predict the probability of locating an electron in a particular energy in a given region of space around the nucleus at a given time gives the concept of orbital. Now, I would like to explain the Compton effect. Compton in 1923 observed that when X-rays of a particular wavelength are allowed to strike on carbon or some other light element, the X-rays are scattered from their original path with lower energy, that is the wavelength of scattered X-rays increases than the incident X-rays. Since scattering of X-rays is due to electron, hence we may say that there is some interaction between X-rays and electron. Due to this interaction, energy of the X-rays decreases. Therefore, decrease in energy or increase in wavelength of X-rays after scattering from the surface of an object such as carbon or light element is known as Compton effect. By applying the laws of conservation of energy and of momentum, assuming that X-rays are composed of photons of energy h nu, Compton derived the following equation: lambda dash minus lambda is equal to h upon mc into 1 minus cos theta, where m is the rest mass of electron, c is the velocity of light, theta is the angle of scattering, h is the Planck's constant, lambda is the wavelength of incident and X-rays, and lambda dash wavelength of scattered rays. Or we can write this: delta lambda is equal to lambda dash minus lambda is equal to h upon mc into 1 minus cos theta, where delta lambda is called the Compton wavelength shift. Evidently, the value of lambda depends upon the angle of scattering theta produced due to collision of X-rays and electron. On substituting different values of h, m and c in the above equation, we can get delta lambda is equal to 0.2424 into 10 raised to the power minus 11 into 1 minus cos theta m. If theta is equal to 0 degree, then cos 0 degree is equal to 1 and delta lambda is equal to 0, that is there is no wavelength shift. So, we can get this: if theta is equal to 180 degree, then cos 180 degree is equal to minus 1 and lambda is equal to 0.2424 into 10 raised to the power minus 11 into 2 meter is equal to 0.4848 into 10 raised to the power minus 11 meter is equal to 0.4848 angstrom. Using Planck's equation E is equal to h nu or E is equal to hc upon lambda, we can calculate the energy of incident and scattered X-rays too. After the failure of the Bohr's atomic model, the scientists were in search of a new model of the atom which could combine the following concept: de Broglie concept of dual nature of matter, Heisenberg uncertainty principle, the idea of stationary energy level for the electron around the nucleus. The atomic model that takes into account the dual nature of the electron is referred to as wave mechanical model of the atom. In 1926, Erwin Schrödinger initiated this model and it was developed by others. If the electrons behave as a wave, then its motion should be described by a wave equation. Generally, wave equation is of second order differential equation, which may be represented as below along the x axis, like this: del square psi upon del x square is equal to 1 upon c square into del square psi upon dt square, where psi is the wave function, x the function of displacement of the string, t is the time and c the velocity of propagation. If the wave propagates in 3 dimensions, then the above equation becomes del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square is equal to 1 upon c square into del square psi upon dt square. where delta square is known as Laplacian mathematical operator, delta is read as del. Although the significance of psi is not so meaningful and reasonable for electron as for the familiar wave motion. In 1926, Schrödinger derived the following equation known as Schrödinger wave equation to describe the motion of the subatomic particle. This equation can be shown on like this, where m is the mass of the particle, E and V total energy of the potential energy of the particle, h is the Planck's constant and psi is the wave function. However, for the solution of this equation, it is more convenient to transform the equation in terms of the spherical polar coordinates expressed in terms of r, theta and phi. The radial wave equation gives the distribution of the electron as a function of distance r from the nucleus. It depends on the values of the two quantum number n and l. Angular wave function determines the shape of the electron cloud or orbital. The complete wave function represents an orbital in which the radial part gives its size and angular part determine its shape. In all wave equation, the square of the wave function is the property which has physical significance. That is, in case of light wave, square of the amplitude of the wave at a point is proportional to the intensity of the light wave. Similarly, in electron wave motion, square of the psi square should represent intensity. According to uncertainty principle, the position of electron cannot be determined with certainty. Thus, psi square may be represented as being proportional to electron density. When psi square is high, electron density is high, that is, probability of finding an electron is high. Solution of Schrödinger wave equation value, which can be real as well as imaginary, but psi square is always real and has a positive value. This is because the square of even negative value is positive. In this lecture, I have discussed about the de Broglie's equation, uncertainty principle and the Schrödinger wave equation, which are in support of the atomic structure. As you know that these are very essential to understand for understanding the atomic structure. Now, in the next lecture, I will discuss about the radial and angular wave function, shape of the orbital and Aufbau principle, Pauli's exclusion principle.